So in our dealings with circuits, we've been talking about resistors and resistance. But now we're going to actually get into what affects the resistance of a resistor or an element or a wire or whatever it is. And so first is just a definition. Resistance is the quality of an object which hinders the movement of free electrons through a material. And the movement of free electrons, that's called current. So it hinders current. The movement of free electrons, we call that current. So we already kind of know this. And the resistance, it depends on four things. It also depends on temperature. So the material that we're talking about, the length of the material and the area, as well as the temperature. So we'll take each of these in turn. The material, we already kind of know. We have two types of materials that we talk about, conductors and dielectrics. So the material, conductors and dielectrics, or insulators. And if you remember when we talked about these, the thing that makes a conductor is it has these free electrons. It has electrons in the outer shells that are able to move between the atoms. Dielectrics, on the other hand, don't, and so we don't have movement. So these are insulators. And so it has to do just with the structure of the atoms themselves. You have these electrons out here that are free to move, and they can jump around between the atoms, or they can bang into it and knock the next one out. It's not that they actually pass through. They just bang and knock ones free, and then they move between the atoms. Dielectrics, on the other hand, these things are bound, so they're not going to move and bounce and do that sort of thing. Some examples of this, conductors, copper is the big one. That's what we use in typical wire. Silver, aluminum, tungsten, and so on. Basically your metals. Tungsten, dielectrics, glass, human skin, plastic, like PVC, water, not that great, but it works. All right, so the material, when we measure the resistivity according to the material, we give it a quantity, it's rho, and it's called the resistivity. And again, this just has to do with the atomic makeup of the material, resistivity. You might also see sigma, which is conductivity. How well does it conduct? Conductivity. So conductivity is actually just 1 over rho. It's the opposite of it. And that makes sense. This is how much it resists it. This is how much it conducts. So you would expect low resistivity, high conductivity, and opposite over here. High resistivity, low conductivity. So what are these? This is the one we'll be using, though, rho, resistivity. So the values on these things for copper, 1.7 times 10 to the negative 8th. So very, very small number. Silver, 1.6 times 10 to the negative 8. 18. So about the same resistivity. This one's actually lower, but the cost of this is much more. So copper, pretty relatively cheap. Well, not really. Anyway, it's cheaper than silver. Aluminum, 2.8 times 10 to the negative 18. And so it seems like aluminum might be a good choice, but aluminum takes a lot of energy to produce. So copper has some other factors with temperature. Let's go to the other side. So glass. Glass is 9 times 10 to the 11th. So you can see the difference, 10 to the negative 18 to 10 to the 11th. Human skin is about, it ranges, it depends, maybe 50,000. The units on this resistivity are ohm meters. ohm meters. Those are the units. But basically that's it. They'll give you these quantities. Okay, so the material, also the length. So the length has an effect on it. So, if we have a piece of wire like so, and then we double the length, how does that change the resistivity? One way to think about it is just at the atomic level. You now have maybe twice as many atoms that it has to bang through to get through this material. And so the overall current that's moving through has been restricted. And so as the length increases, the resistance goes up. So resistance is proportional to the length. Up here, resistance is also proportional to the resistivity. So we have a resistance proportional to length. And this kind of explains, so what that means is if length goes up, resistance goes up. So if we have resistors and we connect them in series, we can now see that what we've done is effectively increase the length. So we've driven up the resistance. Yeah. Okay, so area. If we take the same material and we just increase the diameter of this thing, or the radius, then we've increased the cross-sectional area. And what that's done is it's opened up some space so we can fit more electrons through here in a given unit of time, which would be current. And so we get more current through a wider area. So as area goes up, the resistance goes down. And so we have that the resistance is inversely proportional to the area. You can think about a hallway. So if you have like 10 people, I don't know, or just 2 people, and they're trying to fit through a little door versus a big wide opening, much less resistance if they go this way. There's a lot more room for them to pass through. It's the same idea inside of the material. Now this explains why parallel acts the way it does. So if I have parallel resistors, I didn't increase the length. What I did is effectively I've made those little resistors, I've increased the area if I squeeze them together. I've increased the area which it can go through, therefore reducing the resistance. So we see a drop in resistance across parallel lines. And then we put this all together into our statement, which is that resistance is going to be the resistivity of the object times the length divided by the area. And that's resistance. So now you can use this in Ohm's law. Delta V is IR. So if you don't know the resistance, but we know things about the material, we could do I rho L divided by area. So, for instance, if I knew it was copper, I could use the resistivity of copper, and then I just need to know the length of the wire and the diameter, which will be given by the gauge, and we can figure out the voltage that would be through that wire. But that's basically it. There's really not much to it. Just know the relationship and kind of be able to explain why.